generalized linear models with examples in R. And we're on question 3.26, so chapter 3. So nice simple question here. I have a feeling that, that the author is getting tired of writing questions because this is just really a repeat of a lot of what we've been doing. We're looking at a data set called phosphorus, and we're going to do some things with it. So the first thing we need to do is to install and load the GLM's data package. In that package, there's some data called phosphorus, and so we need to grab phosphorus, and here I'm just calling it D to reduce my typing, and we can get a look at D here, and so we see that we have a data frame with samples, inorganic phosphorus, organic phosphorus, and then PA stands for, I'm not sure, it stands for plant available phosphorus. Okay, so there we have it. Let's go to part 1 here, where we need to plot the plant available phosphorus against both inorganic and organic. So we can do that with our plot command here. Just put in basically the linear model that we'll use, and it will give us 2 plots, one for inorganic and one for organic. So we run that, and we have our 2 plots here. Okay, and we're asked to comment. It's not always easy to be able to comment just by looking at the plots. They look roughly similar, and let's see what else. There does seem to be one guy that might pose a little bit of a problem to the model here. Okay. So number 2 is we're supposed to fit a linear regression model with the systematic component of this, which is what we plotted. So here that is, okay, but we're not asked to do anything with it until part 3, where we are supposed to use t-test to determine which of the covariates is statistically significant. So luckily we have a function called summary, and when we run summary for the model M, we get a lot of stuff, and among them are the estimates for our coefficients, which includes a t-test and the corresponding p-value here. Okay. Just out of curiosity, actually I'm not going to do that. Anyway, but we're not asked any more about it, so we'll just kind of keep moving. And then finally, to use appropriate statistics to identify influential observations and any observations with high leverage. Okay, I think that we can guess that maybe this guy right here is a little bit of a weirdo. But as a first approach, it's always nice just to be able to run the plot function. Okay, so I'm going to run the plot function with M, and when we get that, we get these diagnostic plots. And so we see a few things. So one, we see number 17 is way off the beaten path. Okay, here, 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 and so on. Okay, and we can tell it's influential in a few ways, and one of them is that one, it has a very large residual. Okay, and it is also kind of, at one extreme of, if the x-axis is a teeter-totter, it's kind of way out there. I guess actually that's leverage, but the way that we would actually find influence is to run the regression without it, and then see how that changes things. And then as far as having a lot of leverage, we see that it far surpasses these Cook's distance thresholds that are set, somewhat arbitrarily, but educated. So 17 seems to be influential, and so anyway. But that's really as much as this question is asking, so I'll call that good.